So what do you use for, we use the models for? So we already talked about weather prediction and climate prediction, but now we are talking a lot about climate change. So what is the role of climate models in understanding and the future of climate change? One of the first things is the so-called detection and attribution. So once you have temperature data, for example, it can be any data, could be ecosystem data, greenhouse gas data, and so on. You have a signal that you can infer from observations. This is the anomaly, or the trend over the 20th century into the 21st century of global mean temperatures. So we are looking at anomalies here with respect to some base period, as we said before. So observations show this ups and downs, but they show this steady warming, especially in the last few decades. And the models consider this as the detection of change. As we said before, there are statistical tests that one can do to make sure that the trend is significant statistically, and then you take a model and you provide it all the information it needs. Let's say in a coupled model, all you need to give it is top of the atmosphere radiation, including solar activity like the sunspots and volcanic forcings here like Santa Maria, Agung, El Chichon, and Pinatubo, and see if the models are able to reproduce the observed trend. And you can see that the models with multiple model simulations and the mean of the multiple models, they are able to capture the essence of the trend over the 20th century into the 21st century. We talked about the global warming pause in the 1990s to 2000s, which we are not going to worry about here. But there are differences. Just like we looked at biases, you can see that the observed temperature anomalies show large interannual variability or year-to-year variabilities, including the coolings associated with the major volcanic eruptions. And the models are not expected to produce the same ups and downs in the observations, because models have El Niños and La Niñas and monsoons. Monsoon is a very seasonal thing, so they should produce every summer a monsoon, and they do. But rainfall amounts may be different than observed, as we saw before here. For example, the models have a dry bias, so you can see that models tend to be putting less rain over India in the monsoon region. They put more rain over the ocean, and so on and so forth. They have their own El Niños, and they do happen every few years, and they do peak in December, January, February, just like the real world, except that in the real world there was a strong El Nino in 97-98 here, just before year 2000, and you can see that the models don't capture an El Nino the same year, because these are not predictions. Okay, when we do prediction for 97-98, let's say the prediction starts in January of 97, then most models are able to produce an El Nino because they are initialized coupled forecasts. So for 97-98, many models had very successful predictions. There are details on when the model has to be initialized. If you initialize in January, it has a hard time going through spring months, but if you initialize in May, then the forecasts are more reliable, and the forecasts are skillful for 6 to 9 months ahead of time. So all those sorts of things are there. But in a free integration, the forced variability, or given the increase in greenhouse gases, solar activity, and volcanic eruptions, the models are able to produce the observed trend. This is critical. So what do we do with it? We can then try to see if the detected change can be attributed to greenhouse gas increases by human activities. This is easy to do in the model. So in the model, you can make simulations with all the forcings and see that models are able to reproduce the observed trend. Then you take the model and you remove the greenhouse gas forcings and give it only natural forcing, which means you only give it solar activity and volcanic forcing, and you see that the observations are here and the models without the anthropogenic forcings are down here. So the difference here is recovered by the models when you give it the greenhouse gases emitted by human activities. Okay, so obviously the CO2 has increased from the 1950s to the present, from about I don't know 300 ppm or so to 420 or so. So that explains this difference, which tells us that the warming, additional warming here over this period, can be attributed with confidence to the increase in greenhouse gases due to human activities. Okay, that's one of the most important roles of these models. And such attribution of climate events is done also for intensification of hurricanes, extreme rainfall events, extreme snowfall events, extreme floods and droughts over California, for example, wildfires, and so on and so forth. The next big thing we do with these is the so-called projections for the future. So when you want to project for the future, this is different than predictions. So projections are where you're going into decades, multiple decades. So you need to understand, or at least you need to make up a storyline of how continued emissions of greenhouse gases will occur, how technology may reduce these emissions, how population will increase, how food production will contribute to global warming, how transportation will change, how bioenergy will change, how renewable energies will change, and so on and so forth. So big groups get together and they use multiple models and create what are called representative concentration pathways, and now they're called shared socio-economic pathways. So here we are going from 1980 to 2100. So the black dotted line here, black line with circles, is the observed variability till about 2020, and then you integrate forward with various scenarios. So there are baseline scenarios where you assume no action is taken, or the policies that were implemented in a particular year, like 2005 or 2010, are held fixed, or you assume that newer policies for sustainable development are going to be implemented. So you can see that that changes the net emission of CO2 in gigaton per gigatons total. This must be for year per year. So yeah, we are somewhere in 40 gigaton per year or so, and then in the future, if we don't do anything, we may increase net emissions by a lot. Or if we decide to take action and develop agreements like it happened under Paris Agreement or COP26 that just concluded, and so on, you can find scenarios where the delta F, the radiative forcing, the net imbalance at the top of the atmosphere, can be limited to 6 watts per meter squared, or 4.5 watts per meter squared, or 3.4 watts per meter squared, 2.6 and 1.9. So 1.9 is one of the best scenarios where it allows us to stay in our global warming target of less than 2 degrees centigrade with 67% probability. So multiple models run multiple scenarios, including scenarios on bioenergy and carbon capture and sequestration and other technologies, to show that we will have to reach net negative emissions at some point in the 2050s or so to be able to reach these targets, and other targets will overshoot the 2 degree C warming target and have different ranges of warming. So then you can back calculate, as we said before in the last chapter, how much warming that results in the global mean, and what it may mean at locally for some regions. There are uncertainties or difficulties in deriving local scale changes in rainfall, temperatures, snow amounts, rivers, river flows, droughts, floods, and so on. But we have a good sense of how the global warming translates to statistical changes in these various essential climate variables that we mentioned before. So there are lots of ways, lots of details that go into developing these scenarios, and they cover ranges like this, where you have shared socioeconomic pathways which consider mitigation challenges that go from low to high, and adaptation challenges that go from low to high, and specific scenarios include combinations of these things. So SSP1 focuses on sustainability, so mitigation challenge is low in that case and adaptation challenges are low, but this requires great action on reducing emissions. As you can see, we are already behind. We are already in 2021, close to the end of 2021, so we are not on these pathways yet. Mostly all of the emissions are now on business as usual scenarios, baseline scenarios. So we are pretty much guaranteed to exceed the 1.5 degree centigrade target unless a miracle game changer comes along to suck out CO2 from the air. But we are still able to probably hit 2 degree C warming target if we stay, for example, in the low adaptation challenge, but go after rapid growth, in which case the scenarios become more widespread and we are more likely to hit higher warming. Middle of the road scenarios get us somewhere here. There are other scenarios which assume that regional rivalry is going to be high with global warming, so that raises mitigation challenges as well as adaptation challenges. Or we can keep the mitigation challenges low by doing various, let's say, geoengineering kind of approaches, but adaptation challenges may remain high, leading to inequalities and so on. So all kinds of detailed storylines or narratives are used to build these scenarios, and there are details that when you do these projections at the outer years, the scenarios determine where you end up, but in the early period for the next decade or so, decade or two, the model biases and uncertainties that we mentioned, they tend to dominate the evolution of temperatures and hence related changes in extreme events, glaciers, sea level rise, etc., even climate and health, for example. Okay, so I will leave this here and then come and add another podcast on where we are headed in terms of some of the projections and how the models have improved since the last projection. So the last projection was made in 2014, called Assessment Report 5. Assessment Report 6 is already being released. Draft version of the physical basis for climate change has been released. These assessment reports are largely a synthesis of all the related relevant science on global warming that's been done since, and these kind of projections which are done as coordinated activities under IPCC, and it is managed by the World Meteorological Organization. WMO runs the so-called CMIP6 simulations, which are Coupled Model Intercomparison Project version 6. Okay, so the model versions have evolved over time, and they are much higher resolution with much more complexity and details of representations compared to earlier versions used for earlier projections. Okay.